Today we're going to look at adding a real-time clock module to the Pi Pico. There are various reasons why you might want to add a real-time clock module. You might be using the Pi Pico to do data logging, or you might be running crypto functions that require an accurate date and time. In this case, I chose the DS3231. Reasons being it can be powered by a 3.3 volt source, which is available off the Pi Pico. It uses an I2C interface, which works well with the Pi Pico, and many of the modules that are available on the market come with battery backup installed on the module. So you can kind of see here the module that I've chosen. It has the chip on it there. We can get in focus. Has the DS3231 chip, a small battery backup, and then a handy little connector there so that you can hook it up to the Pi Pico. You can see there it has the power connections, plus voltage in, the ground, and then data and clock lines for the I2C connection. Looking at the data sheet for the DS3231, we can see the different registers that are available through the I2C interface. We'll mainly be interested in the first 7 registers that are used for the actual clock. The remaining registers are reserved for a couple of alarms and then some other features that are supported by the DS3231. It's important to note, looking at these registers, that the numbers are stored in binary coded decimal, BCD. So that means that the first 4 bits of a register are used to represent the first digit, and then the next 4 bits are used to represent the second digit, the tens digit. So bits, looking at register 0, bits 0 through 3 can count from 0 to 9, and then when it rolls over, bits 4, 5, and 6 in the upper part of the register are used for the tens location. So you can see 10 seconds and then just seconds. We can see the same thing in the minutes register, where 00 through 59 are represented again binary coded decimal, the minutes in the lower 4 bits and the 10 minutes in the upper 3 bits. Just to note, the reason why they're not using the most significant bit, bit 7, is because the time will roll over, right? Obviously 60 seconds, 60 minutes, it doesn't go over 59, so there's no need to use the last bit on the register. On the hours, it gets a little more interesting because the clock can keep track of time in either 12 or 24 hour intervals, and so it's still BCD to where the first 4 bits are the hour, and then the 4th bit is the 10 hour, and then the 5th bit will be used for either the 20th hour, or it designates AM PM, depending on whether or not you're using 12 hour or 24 hour intervals. And then they have a register to represent the day of week, so it only uses the first 3 bits so that it can represent the day of week from 1 to 7. It's interesting to note on this register that the number is actually arbitrary. So the DS3231 does not specify what day of the week is 1. So that's up to the programmer to decide, and then you set the register appropriately. And then the date of the month, again BCD, so the first 4 bits are the 1's digit, and then it uses the 4 and 5 bits to represent the 10's digit, which could be anywhere from 0 to 3. Oops, sorry, 3. And then we have the month, which, again, this register has some additional purposes. So for the month, it's BCD, so the first digit of the month is in the first 4 bits, and then the 5th bit is used for the tens digit. And then the last bit on this register is used to designate what century that the clock is running in. So from the year 1900 to 1999, this bit would be 0. And then for the years 2000 to 2099, this bit would be 1. The reason for that is that they can't represent years over 99. And we'll see that in the next register where the year is stored. Using BCD and a single register, we can only store a number from 00 to 99. And so that's why we need all the bits in this register in order to represent 99. And so we need an additional bit in the month register to designate what century we're in. So does the number 00 through 99 represent the year 1900 through 1999, or the year 2000 through 2099? And then after that, so that's the last register. These remaining registers are all used for alarms. There's 2 alarms on it, and then some additional features on the chip. Now, looking at the circuit diagram, it's fairly simple since we only need power and an I2C interface. You can see here where we have the ground from the Pi Pico set up on a rail on our breadboard. One of the grounds goes to our reset button, and then we have a ground line that goes to our DS3231 module, and then 3.3 volts out from the Pi Pico is connected to the other rail on our breadboard, which is then powering the DS3231. So when the Pi Pico is on, it will power the module, and then when it turns off, the module will use the backup battery to keep track of time. It'll go into like a sleep mode where it's still operating but at a low power mode. And then in this case, you can see where I have the data signal from for the I2C data signal from GP4 and the clock signal from GP5 connected to the I2C interface on the module. Many people might have hooked it up to the I2C interface that's on pins 1 and 2, but in my case, you'll see when we get into the actual circuit, I'm using these for a UART interface. So here you can see the actual circuit. So we have the DS3231 here, and we have our Pi Pico, and in this case, this is the same circuit that was used for the Pi console circuit, where we have a manual reset button to reset the Pi Pico, and then I have a UART connection here that's using the first I2C interface on the Pi Pico, and I use this as for a console, and this will make more sense as we get into the code and actually start using the module, because you need some way to actually communicate, set time and read time from the real-time clock, and I'll be using commands in the Pi console that is connected to this UART interface. So on the DS3231 itself, you can see where we have our ground line, which is connected to the ground on the Pi Pico, and then we have 3.3 volts to power the DS3231 module that is also coming from the 3.3 volt output from the Pi Pico. So whenever the Pi Pico is powered on, it will also power on the DS3231. And then of course we have the 2 lines for our I2C interface, the clock and data signals that are running over to one of the I2C interfaces on the Pi Pico. So we'll be using GP4 and GP5 for that interface. So I'm using the same setup as the previous videos. I have a Linux workstation here with the Pico SDK installed. Everything's set up to do my Pi Pico coding. This project is based off the Pi Pico C console project in the previous video. So some of this should be familiar if you've watched that video. And in fact, the code started with the Pi Pico C console project, and then added functions to interact with the DS3231. So let's go ahead and grab the code from GitHub. And the project is Pi Pico C RTC for Real Time Clock. Git. Okay, let's go into project directory. Okay, so this just has the source code in it, so we need to make our build directory, cd into our build directory, and of course we need to export a path variable so that it knows where the Pi Pico SDK is located. So export Pico SDK path is equal to home directory embedded Pico SDK. Okay, so from this point we can just run cmake from the directory below. Should build everything. And okay, so cmake is finished, and now we just need to make the binary. So this should compile everything we need from the Pico SDK and our clock program, and then we can load that up on the Pi Pico. And there we go. So ls, the program is clock uf2. So we can just go down here and reset and boot select. Okay, we are now mounted, so we can copy the clock uf2 file to run media rpi2, and there it is. So now that the clock program is loaded up on the Pi Pico, we can go ahead and use our console program. In this case I use screen, connect to the console device. In this case, since I'm using the UART, it will be a USB device, and we need 115K. So there we go, console's up and running. If I type help, and we can see the commands that are available from the console, and there are two new commands that were added to the Pi console, the time and set Zulu. So if I enter command time, it will show the time from the DS3231. When you first power on these devices, it's going to come up with just all zeros stored in the device, and then from that point on it will start to count the time, as long as it has a battery backup or power attached to it. So obviously the date and time are incorrect, so we can use the other command, set Zulu, to set the UTC time on the device. So it's currently year 2023, February 26th, and the time is 5 p.m. so 17, and I set up the code to run in 24-hour intervals. So the device, it will automatically configure it when I set the time to make sure that it's counting in 24-hour intervals. So 17, and it's currently 25 minutes after, and we'll just put 00 seconds Zulu time. And now if we ask it again what the time is, and there we go. So we now have the correct time. Time. And it should just continue to count up. And then of course the important part is, so now if I power down the Pi Pico, so right now we have the USB connection that's providing power to the Pi Pico, which in turn is providing power to the DS3231. So if I pull this, we have now lost power to the Pi Pico and to the DS3231. But theoretically, being a real-time clock with a battery backup, it should continue to count. And just so you can see, my console should be, gone. So obviously with no power on the Pi Pico, I can't do anything. Of course, the UART is still running, but there's nothing for the UART to talk to. So if we go ahead and power the Pi Pico back up, and there you go, you can actually see the console already came alive. It's pretty quick. And in the code we'll see later, when it powers on, it does some initialization just to make sure that the DS3231 is working, and obviously to set up the I2C interface to talk to it. So the last time we were talking to it and we asked it for the time, you can see we got February 26, 17, 25, and 15 seconds. So if we ask again, you can see obviously, so 17, 26, 49. So even though it was powered off, the clock continues to count up. Okay, so let's take a look at the actual C code for the real-time clock. Again, this is based off of the C console. So some of this will be familiar if you'd seen that before. And I'm actually just going to go over the clock functions, not the entire thing. If you want to know more about the console, then check out the previous video and the GitHub project for the Pi Pico C console. But if we look inside our project here, you'll see that there's a new header file and C file for the DS3231. It's declaring some settings and some functions that will be used to communicate with the DS3231. But in the console code, or sorry, not the console, but the command code for the console, I've added in this including the header for the DS3231, so that the command will know about the DS3231. And then there are now these new functions in the command. So there's a function to display the time, set the Zulu time, and then there are a couple of additional methods that are used for validation of the string that you're entering when you want to set the time. So if we go look at the C code for the command itself, of course we have a new help message to let you know about the two new functions that are available in the command console. And then in the command processor, when it starts up, it initializes the DS3231, and we'll go look at that in a little bit, but basically sets it up for I2C communication and some other things. But in the command console, of course, as before, it's going to wait until there's a command ready to be processed, and then it checks to see what is the command. Is it help? Is it boot ROM? And then we have the new console command time to display the time. So if you enter time, it's going to run the function display time. And if you enter the command set Zulu, then it's going to run the command set Zulu time. And of course it also is looking for set Zulu as well as a string, because you need to provide the string that is the time. And there's an additional command here that is not documented, and we'll talk about this a little bit. This is to set the day of week in the DS3231. As you recall, the value in the DS3231 is arbitrary. It's kind of up to the programmer to decide what day of the week is the start and end for the numbers 1 through 7. And we'll go over that in a little bit. But this is just a command that I put in there to do some testing to manually change the day of week and see what the effects are. So if we look, when you request the time command and it calls display time, we have the display time method, which creates a date time structure and passes a reference to the read DS3231 time. This is one of the methods in the DS3231 code, the header file. And so this will read the time out of the DS3231 and then populate this date time structure. As long as status is okay, that it didn't have an error. Well, if it had an error, it's going to print the error. But if it doesn't have an error, then it will just print out a formatted string with the time that is in the date time structure that was set by the read DS3231 time. And then, of course, the other command, set Zulu, is going to call the function set Zulu time with a pointer to the string that is the string you entered. And same thing, this is going to create a date time structure, and then it's going to parse out the values that you entered into the string and populate the well, not populated yet. It's going to just set some variables. So it parses out the year, the month, day, the hour, the minute, and the seconds from the string that you entered. And then with those values, it will then populate the time structure with the appropriate values based on the, if you read the C specification for struct TM, then you can see what the values need to be in there. So they're set based on the values parsed from the string. And then there's some validation just to make sure that it looks like it's a valid, the values are valid that you had entered. Because there's no checks here, and there are no checks here to see if you're entering correct values. So once it's parsed all the values, populated the time structure, then it just does a validation to make sure that what's in there is correct. And then this part, so here we kind of get into some of the day of weeks things. So you'll notice, if you go look at the specification for the struct TM structure, there's a value for the weekday and there's a value for the year day. However, we don't get those from the ISO string that you enter to set the Zulu time. So we kind of use a little bit of a trick here to where we take the date time structure that you entered and convert it into a time t value, and then we create a new time date structure based off of the value that MakeTime extracts from the date time that you entered. And the reason for this is that this date time structure that you entered does not have the weekday or the year day, but we can still convert that into a time number, and then when we convert that time number back into a new time struct, it will actually set the weekday and the year day for us. And you'll see when we get to the DS3231 function to set the time, we don't actually need the year of day, but we do need the weekday. So that's what this is all about, just a little bit of a trick to get these values that are not set by the string that you entered. So once we have this converted new time date structure, we call these set DS3231 time with that structure, and theoretically, as long as we don't get an error, then once it returns, the time in the clock should be set. And then don't need to really go over these, you could probably look at them yourselves. These are just the string input validation functions to make sure that it can parse it correctly. So if we go look at the code for the DS3231 itself, first thing is, so if you recall, when the command processor starts up, first thing it does is it initializes the DS3231. So it calls this method, and as noted, you can see it's setting up the I2C interface. So if we can go look at this in the header file, and I mentioned this before. So it defines in here which pins are being used for the I2C interface and which interface it is. Also sets up the I2C address of the DS3231, and then just some additional settings that you can probably take a look at on your own. But once it initializes the I2C interface, it calls this method adjust DS3231 day. The reason for this is that most of the times it's not really necessary, but with a a fresh DS3231 module installed on the Pi Pico, even though it may have a correct time and date, the day of week may or may not be correct for the system that it's running on. And so when it starts up, it calls this method to ensure that the day of week is correct. So if we go look at this function, it kind of does something similar to what the command function was doing when it parses out your string. So we have a datetime structure. It reads in the current date and time from the DS3231 into our datetime structure, and then just makes a note of what is the weekday number currently returned by the read time function. And then it uses that date time to again create a time number, and then uses the GM time to again take that number and turn it into a new time struct. So we're going to take this new time struct, which once you run this GM time on that time, it's going to set the correct TM weekday and TM year day. And what we're interested in is the TM weekday. So what we do next is we just do a comparison to see, is the day value that we had received from the initial read of the DS3231, is it different from the TM weekday value? And if it is different, then we know that it's not correct and it needs to be adjusted. So to adjust it, we just set the time with this new time, which should have the correct TM weekday in it, which is day of the week, and that should correct if the day of week is wrong, and then just returns the status of that. So that's the initialization, what the initialization does. So the command prompt, when you enter time and you want to see what the time is, it's going to call the read DS3231 time method, and it's passed this a pointer to this time date struct. And so then we begin the process of reading what is the time in the DS3231. So this variable here is just being used to specify the start register where we want to start reading, which we want to start at the very first register in the DS3231. Just a status variable for the results. We need to define a buffer that we will use to hold the contents of the registers when we read, and here we're just resetting the buffer, just setting a value of 0 in all the positions of the buffer. And then first thing we do is we do a write. So we do a write of this register value of 0. So basically we're sending a 0, 0, and we're just writing 1 byte to the DS3231. And what this is, if you read the data sheet, you write to the DS3231 with the register where you want to start reading or writing. And since we're only writing 1 byte, it's only going to send just the register where we want to start. So it's going to set the DS3231 pointer at register 0 for the next operation. And of course the next operation is going to be a read. So we're going to read all the time registers from the DS3231 into our buffer that we created, and then we just check our status. We should get a 0. If we don't get a 0, if we get an error code, then we're going to return that error code. Otherwise, if it succeeded in reading the registers into the buffer, we call buffer to time, which takes the buffer values, which are the registers from the DS3231, and uses them to populate the date time structure. And then, assuming that's all successful, we return a no error code, and the date time should be populated. Now if we go look at this buffer to time, and maybe we don't want to go too deep into this, but basically all it's doing is it's taking the information that we read from the data sheet on each register and using that information to populate the date time structure. So as you recall, the registers are in BCD, binary coded decimal. And so if we just look at like the seconds, we know that the first 4 bits hold the seconds, the 0 to 9 seconds digit. And so we're setting a variable temp with the value that's in buffer 0, and then we AND it with 0f. What this does is just extracts the first 4 bits out of that register that's been stored in temp and stores them into the seconds setting in the date time structure. And then we shift the temp value 4 bits to basically shift off the first 4 bits, and then the last 4 bits will be at the start of the byte. So then we have to multiply by 10 because we're now on the tens digit 10 times, and then we only use the first 3 bits of that part of the register. And it's similar, this similar action is taken on almost all of the registers because they're all BCD encoded. So it's basically just going register by register and setting them up, reading them and converting the BCD into an actual decimal value in our structure, in this case the minutes right here. Some of them get kind of interesting because as noted before, if the clock can be running, the DS3231 clock can be running in a 12-hour or 24-hour mode. And so this code will just handle it. It'll read the settings, the values from the registers, and produce the correct time hour based on whether it's in 12-hour or 24-hour mode. And then day a week, the same thing. It's all BCD. And then the one area where it starts to get odd again is, if you recall, the month includes not just the BCD number for the month, but it also holds a bit for the century. And why am I not seeing? Oh, yeah, here we go. Sorry. So the temp value is loaded with the month register, which is in the buffer register 05. We extract the first digit for the month, then we extract the second digit from the month, and then we just have to adjust because the values, the way they're stored, in one case they're stored month 1 through 12, whereas in the date time struct it's stored 0 to 11. But now we take this, the value that's in temp, and we check to see here if the most significant bit is set by ANDing it with a 0x8. And if the bit is set, then we know that it's in the 2000 century. If the bit is not set, then it's in the 1900 century. So we need this information for the following register, where we get the year that will be 00, somewhere between 00 and 99, and then we can add to that, well, yeah, we already have our century in the year variable, and then we just add the 00 values to the time year. And then to get the Unix timestamp, we subtract then again 1900 from it to complete it. So that's that's converting the registers in the buffer to the time date structure, which is then returned to our time request in the command. And then of course the other command is to set Zulu time. Again, it's passed a date time structure, and then we go through a process very similar. So we create a buffer, load the buffer with zeros, and then we use the time to buffer method to take our date time structure and populate the buffer. The reason why this is +1 is because again, we're going to use this buffer to write, and the first byte in the buffer actually specifies the starting register where we want to begin writing. So we want to start writing at register 0, so we have the first byte in this buffer will be 0 because we reset everything here, and then the remaining 7 bits will be the registers that are going to go into the DS3231. So this time to buffer function is basically, here you go, it's going to take the values and again convert them from the decimal values into BCD values. So BCD for the year, then we need to extract the century bit for the month, BCD, just on, and then we take these BCD values, converting from the decimal values in our date time structure into BCD values, and then storing the BCD values into the different buffer registers. So buffers 0 through 6, and again, remember the pointer that we passed in here is +1. So we're actually, even though this is 0, we're at register, well, not register, but position 1 in the buffer, 1 through 8. So once it populates all the BCD values from the time to buffer, it will return. And so now that the buffer is loaded with the starting register and then our 7 register values, then it just writes to the DS3231. So, and pretty simple. These are just I2C writes. Same thing with, we didn't look at this, but the read method, just doing I2C reads. So just in one case, reading from a buffer and writing to the DS3231. In the other case, just reading from the DS3231 into a buffer. And there's actually, there's probably more that we could go over in this, but most of it is just logic in order to make calculations and whatnot. But yeah, feel free to grab a copy of the code and try it out. So let's just do this again, time. So you can see the time is still counting there. It's keeping track of the time with the real-time clock on the DS3231. And that's it.